Hello friends, welcome to 90 Plus My Tuition app. Swiss mathematician Leonhard Euler developed the notation for functions and trigonometric functions. The base for all the functions are relations. So today we are going to discuss about this in our chapter. Chapter 1, Relations and Functions. So what is relation? If there is any connection or link between the elements of any sets, then those sets are related. Now, let's take two sets, set A and set B. The elements of set A is Rahul and Ram, and the elements of set B is cat and dog. The information we know is Rahul has a cat and dog, and Ram has a dog. So, how do we define a relation here? That is, relation R equal to set of ordered pair A comma B such that A has a pet B. Now, what all are the elements in the set R? That is, R equal to ordered pair Rahul cat, Rahul dog and Ram dog. That is, we got three elements in the set R. Now, let's move on to our next topic, types of relation. Before that, what is Cartesian product of set A to set A? For that, let's consider set A with elements A and B. Now, what are the elements of the Cartesian product? It is set of all ordered pair A comma A comma B, B comma A and B comma B. That is, it is the collection of all relation of set A to set A. That is, if we take any relation, it will be the subset of A cross A. So, now we are going to study different kinds of relation. So, the first one is empty relation. For that, let's consider set A equal to 1, 2, 3 and 4. And let's define relation R equal to set of ordered pair A comma B such that A minus B equal to 10. So, my question for you guys is whether we will get 10 by subtracting any two elements from the set A. Let's check that. So, what is the highest number? It is 4. And what is the lowest number? It is 1. So, let's subtract 1 from 4. That is 4 minus 1. Which gives you 3. That is, we won't get any ordered pair as element from the relation R using the set A. That is R equal to 5. That means R is null set, and this is called as empty relation. Now our next extreme relation is universal relation. For that, let's consider set A with elements 1, 2, 3 and 4. And let's define relation R dash equal to set of ordered pair A comma B such that mode of A minus B is greater than or equal to 0. So our condition is modulus of A minus B is greater than or equal to 0. That is, if we subtract any two elements and then apply modulus, we will get the number as positive. That is, if we take any two elements from set A, this condition will satisfy. That is, all the ordered pair of set A to set A will be present in the relation R dash. So, we can write R dash as A cross A. So, our two extreme relations are empty relation R equal to 5 and universal relation R dash equal to A cross A. Now, let's solve some problems using these types of relation. So, our first question is, let A be the set of all students of boys' school, and relation R is defined as set of ordered pair A comma B such that A is sister of B. So, how do we solve this problem? For that, let's consider two students, A and B. So, in the question, it is given that all students are boys, but relation R is defined as A is sister of B, which means that A cannot be sister of B. That is, the number of elements in relation R equal to 0, which means that R will be equal to 5. That is, R is empty relation. Moving on to the next question. Let A be the set of all students of boys' school, and relation R dash is defined as set of ordered pair A comma B such that the difference between height of A and B is less than 3 meters. We know that height of school boys cannot be 3 meters. Let's consider two students, A and B. Let A be the tallest boy and B be the shortest boy. Even then, the height difference of A and B will be less than 3 meters. That is, if we take any two students from the school, the height difference will be less than 3 meters. That is, R dash will be equal to A cross A. That is, R dash is universal relation. Moving on to the next topic, equivalence relation. Before knowing that, we need to know three types of relation, namely reflexive, symmetric and transitive. So what is reflexive? That is, a relation R in set A is called as reflexive if ordered pair A comma A element of R for every A element of A. Then what is symmetric? That is, if ordered pair A1 comma A2 element of R implies that ordered pair A2 comma A1 element of R for every A1 comma A2 element of A. Then what about transitive? That is, if ordered pair A1 comma A2 element of R and ordered pair A2 comma A3 element of R implies that ordered pair A1 comma A3 element of R for every A1, A2, A3 element of A. Now let's solve some problems. So our first question is, let T be the set of triangles in a plane with R a relation in T given by R equal to set of ordered pair T1 comma T2 such that T1 is congruent to T2. Show that R is equivalence relation. So what is T? T is the set of all triangles in a plane, and relation R is defined as if any two triangles are congruent, then it will be the element of R. Now, when do we say two triangles are congruent? That is, if the sides and angles of one triangle is equal to the corresponding sides and angles of another triangle, then we say the two triangles are congruent to each other. Now, what are the conditions for equivalence relation? The first one is reflexive, the second one is symmetric, and the third one is transitive. Now let's check for reflexive property. We know that a triangle is congruent to itself. Thus, we have proved our first property, that is reflexive. Now let's check for the next property, symmetric. Let ordered pair T1 comma T2 element of R, that is T1 is congruent to T2, which implies that T2 is congruent to T1, that is ordered pair T2 comma T1 element of R, that is T1 is related to T2 and T2 is related to T1. Hence the relation R is symmetric. Now let's check for transitivity. Let ordered pair T1 comma T2 element of R and ordered pair T2 comma T3 element of R, that is T1 is congruent to T2 and also T2 is congruent to T3, which means that ordered pair T1 comma T3 element of R. Hence we have proved that R is transitive. Hence the relation R is equivalence relation. Moving on to the next question. Let L be the set of all lines in a plane and R be the relation in L defined as R equal to ordered pair L1 comma L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive or transitive. That is, L is the set of all triangles in a plane and the relation R is defined as ordered pair L1 comma L2 such that L1 is perpendicular to L2. That is, all the perpendicular lines are related according to the question. So we have to prove that the relation R is symmetric but neither reflexive nor transitive. So let's check for reflexivity. For that, let's draw a line L1. Here we have to check whether L1 is related to L1. But in the question it is given that L1 is perpendicular to L2. That is, the angle between L1 and L2 is 90 degrees. But we can clearly see that L1 is making 0 degree angle with L1. So ordered pair L1, L1 not element of R. That is, R is not reflexive. Now let's check for the next property, that is symmetry. For that, consider another line, that is L2. Let ordered pair L1, L2 element of R. That is, L1 is perpendicular to L2. That is, angle between L1 and L2 is 90 degrees. That is, L2 is perpendicular to L1, which implies that R is symmetric. Now let's check for transitivity. That is, ordered pair L1, L2 element of R and also ordered pair L2, L3 element of R. Now draw another line L3. That is, L1 will be perpendicular to L2 and L2 will be perpendicular to L3. That is, L3 will be perpendicular to L2, which implies that L1 is perpendicular to L2, also L2 is perpendicular to L3. Now we need to check whether L1 is perpendicular to L3. We know that L1 is parallel to L3 here. That is, L1 is not perpendicular to L3, which implies that ordered pair L1, L3 is not element of R. Thus, we have proved that R is not transitive. That is, we have proved that R is symmetric but neither reflexive nor transitive. Moving on to the next question. Consider the set A with relation R and set A equal to 1, 2, 3, 4, 5 and 6. And relation R is defined as ordered pair A, B such that A divides by B. So the first question is, write all the elements of R. And the second question is, show that R is reflexive. And the third one is R an equivalence relation? Justify your answer. From the question, it is given that R is defined as if you take any two elements from set A, namely A and B, then B by A should be an integer. Now let's solve our first question. That is, write all the elements of R. That is, set A equal to 1, 2, 3, 4, 5, 6. So we need to check all the elements which are related to each other. So first let's take the first number 1. We know that 1 divide with all elements. That is, 1 divide with 1, 2, 3, 4, 5 and 6. So we got the first 6 element of set R. That is equal to set of ordered pair 1, 1 and set of ordered pair 1, 2 and set of ordered pair 1, 3, ordered pair 1, 4, ordered pair 1, 5 and ordered pair 1, 6. Now let's take the next element, that is 2. Numbers that can be divided by 2 will be the multiples of 2. And we know that the multiples of 2 are 2, 4 and 6. So set R will contain ordered pair 2, 2, 2, 4 and 2, 6. Now take the next element, that is 3. 3 divides its multiple 3 and 6. So set R will contain ordered pair 3, 3 and 3, 6. Now take the next element, that is 4. The multiple of 4 is 4 itself. So set R will contain ordered pair 4, 4. Similarly, for 5 and 6, the multiples of 5 and 6 is 5 and 6 itself. So set R will contain ordered pair 5, 5 and ordered pair 6, 6. Now we have written all the elements in the set R. So moving on to the next sub-question, that is whether R is reflexive. By seeing the elements of R, we can clearly see that ordered pair 1, 1, ordered pair 2, 2, ordered pair 3, 3, ordered pair 4, 4, ordered pair 5, 5 and ordered pair 6, 6 are the elements of the set R. That is, R is reflexive. Moving on to the next sub-question, is R an equivalence relation? From the previous question itself, we have proved that R is reflexive. Now we have to prove that whether R is symmetric and transitive. Now let's check for symmetric condition. For that, let's take ordered pair 1, 2 from set R. And it is clearly seen that ordered pair 2, 1 is not element of R. Hence, it is proved that R is not symmetric. And we know that if any one of the condition does not hold means R is not equivalence relation. Hence, we proved that R is not equivalence relation. Now, let's move on to our next topic, that is equivalence class. Consider a relation R that is defined on set A, which is equal to 0, 1, 2, 3 up to 16. A is related to B if A minus B is a multiple of 4. Here in this question, we need to prove that it is an equivalence relation. For that, we have to check 3 conditions, that is reflexive, symmetric and transitive. Here, relation R is defined as if you take any 2 elements from set A, then their difference will be a multiple of 4. So, let's check for the first property, that is reflexivity. Let A be the element of A. We know that A minus A equal to 0. That is, 0 is a multiple of 4. That is, all the elements are related to itself. So, we can say that ordered pair A, A element of R. That is, R is reflexive. So, moving on to the next property, that is symmetry. If ordered pair A, B is element of R, we need to prove that ordered pair B, A element of R. We know that if ordered pair A, B is element of R, then A minus B is a multiple of 4. Now, let's take an element from set A, that is 8. 8 is a multiple of 4. That means minus 8 is also multiple of 4. Similarly, 16 and minus 16 is multiple of 4. That is, if A minus B is a multiple of 4, then we can write minus of A minus B is a multiple of 4. That is, minus A plus B is multiple of 4. Rearranging this, we will get B minus A is a multiple of 4. That is, ordered pair B, A is element of R. That is, ordered pair B, A is related, which means that R is symmetric. Moving on to the next property, that is transitive. Let ordered pair A, B element of R and ordered pair B, C element of R. That is, we can say that A minus B is a multiple of 4 and B minus C is a multiple of 4. That is, if we add the multiple of 4, then the result will be a multiple of 4. So, adding, we will get A minus B plus B minus C is a multiple of 4. So, cancelling plus B and minus B, we will get A minus C is a multiple of 4. That is, ordered pair A, C element of R, which means that R is transitive. Now, let's check for equivalence class. We need to find the elements that are related to 0. That is, A is related to 0, which implies that A minus 0 is multiple of 4. That is, elements that are related to 0 will be the multiple of 4. We know that the multiple of 4 are 0, 4, 8, 12 and 16. So these numbers are related to 0. Now let's check for the elements that are related to 1. That is, A is related to 1, which implies that A minus 1 is multiple of 4, which implies that A minus 1 is M of 4. That is, A equal to 1 plus M of 4. That is, adding 1 to the multiple of 4, we will get A. That is, we will get 1, 5, 9 and 13. Now let's check for the elements that are related to 2. That is, A is related to 2, which implies that A minus 2 equal to M of 4, which implies that A equal to 2 plus M of 4. That is, adding 2, we will get 2, 6, 10 and 14, and these are related to 2. Now let's check for the 3. That is, A is related to 3, which implies that A minus 3 equal to M of 4. That is, A equal to 3 plus M of 4. So we will get 3, 7, 11 and 15. Now let's divide these into 4 sets. First one is A0, which is equal to 0, 4, 8, 12 and 16. Then A1, which is equal to 1, 5, 9 and 13. Next is A2, which is equal to 2, 6, 10 and 14. Now A3, that is equal to 3, 7, 11 and 15. So what is A0? A0 is a set of elements that are related to 0. What is A1? A1 is a set of elements that are related to 1. And what is A2? A2 is a set of elements that are related to 2. And what is A3? A3 is a set of elements that are related to 3. Now, what about AI? AI is a set of elements that are related to I. From this, we can conclude that all the elements present in the set A is present in these sets. That is, all elements of set AI are related to each other. Also, we can say that any element of AI is not related to any element of AJ if I not equal to J. That is, if we take any two elements from any two distinct sets, then the elements are not related if I not equal to J. Also, we can say that each sets are mutually disjoint sets. Also, if we combine the elements of A0, A1, A2 and A3, we will get set A. That is, A0 union A1, union A2, union A3 equal to A. And it is also found that AI intersection AJ will be equal to null set if I not equal to J. That is, we call set A0, A1, A2, A3 as equivalence class. The equivalence relation R divides set A into 4 mutually disjoint sets, and we call it as equivalence class. That is, if we take the union of these sets, we will get set A. That is, A equal to A0 union, A1 union, A2 union, A3. From this, we can say that 0 is element of A0. That is, all the element of A0 is related to itself. That is, all the element of set A0 can be called as equivalence class, and set A0 can be written as equivalence class of 0, and we denote it in box bracket. That is, A0 equal to equivalence class of 0, which is equal to equivalence class of 4, etc. And A1 equal to equivalence class of 1, which is equal to equivalence class of 5, etc. And A2 will be equal to equivalence class of 2, which is equal to equivalence class of 6, etc. And A3 equal to equivalence class of 3, which is equal to equivalence class of 7. That is, we can partition any relation of set A into equivalence class. Now let's move on to the properties of equivalence class. Equivalence class divides set A into mutually disjoint sets. That is, we cannot see intersection between sets. That is, if we take the union of equivalence class, we will get set A. Now let's move on to the definition of equivalence class. That is, suppose A is element of A, then set of all elements of A related to A is the equivalence class, and it is defined by equivalence class of A equal to set of A element of A such that X is related to A.